Dear colleagues, I would like to introduce a report called Space Optical Interferometer Gravitation Antenna SOIGA based on GLONASS orbits. Present registration of gravitational waves is one of the most promising and rapidly developing area of astrophysics. The result of work on creation and improvement of ground-based gravity detectors for almost 50 years was the world's first registration of gravitational waves in September 14, 2015. By two detectors of laser interferometer gravitational wave observatory LIGA. The main disadvantage of ground-based gravitational wave observatory is the significant noise caused by seismic effects. In addition, due to the limited arm length of interferometer currently used and planned ground-based gravitational waves observatories can detect gravitational waves in frequency range from 10 to 1000 Hz. Space gravitational waves observatories are free of above-mentioned disadvantages of ground-based detectors and can detect gravitational waves with frequency below 10 Hz. The most promising projects are LISA with approximate launch year 2034 and SOIGA and Denisenko with approximate launch years from 2030 till 2040. The review of space gravitational wave antennas shows that they mostly detect gravitational waves with frequency below 0.1 Hz. So the frequency range from 10 mHz to 10 Hz has the lowest coverage by both ground and space detectors. Project SOIGA is proposed to detect gravitational waves in this frequency range. The arm length of SOIGA interferometer shouldn't exceed 100,000 km. So it is possible to place antenna on geocentric orbit compared to LISA, Lagrange and Denisenko located on heliocentric orbits. The advantages of gravitational wave antenna location on geocentric orbit are the next. First is communication with Earth that requires less power and small antennas as the spacecraft is much closer to Earth. The second, there is no need to develop a special ground-based stations for spacecraft control and signal reception, as they have already been created to service existing near-Earth orbital constellations. It also takes much less fuel and time to launch satellites into heliocentric orbits that reduce cost of the project. The existing long-term experience in the launching of satellites will ensure the reliability of spacecraft mission and significantly reduce the cost of project development and implementation. The first concept of SOIGA project was reported in the article listed at the bottom of the slide. There were two spacecraft configurations. The first one is orthogonal. Three spacecrafts form two arms of interferometer. The length of the arms is about 36,000 km, and the arms are orthogonal to each other. That provides maximum efficiency of gravitational wave observatory. In such scheme, the third laser communication line is impossible because it crosses the Earth. The second configuration is called triangle. It also consists of three satellites on GLONASS orbit. In this case, the angle between the arms of interferometer is 60 degrees, and the length of interferometer arm is 43,000 km. In this configuration, three measurement interferometer arms can be implemented. The GLONASS system consists from 24 satellites located in three identical orbital planes with inclination of 64.8 degrees, an orbital altitude of 19,000 km and an orbital period of 1 hour and 50 minutes. The main advantages of choosing GLONASS for gravitational wave observatory location are the following. The orbital position of GLONASS satellites is quite stable, as their orbits have no resonance synchronization with Earth's rotation. Significant experience has been accumulated in the GLONASS in the following areas. In terms of conducting high-precision radio engineering and laser trajectory measurements along the Earth satellite and satellite lines. In terms of operation of highly stable onboard atomic satellite clocks with a stability of 10 to minus 14 power as in terms of space system synchronization. In terms of scientific and technical groundwork for the production of GLONASS satellites, components and their launch and maintenance. To improve the sensitivity of SOIGA project and improve the accuracy of gravitational wave source location and determination of gravitational wave polarization, 3 different satellite configurations were proposed. In the first configuration, 4 spacecrafts are located in the plane of one orbit at the vertices of the square. The advantage of this configuration is the response, which is 4 times bigger compared to orthogonal configuration, as each side of the square can be measured by 2 different interferometers independently. The second configuration is called Octagon, which consists of 2 constellation square spacecrafts deployed at 45 angle relative to each other. This configuration allows to improve the detector response to gravitational wave with H+ and H cross polarization. The third configuration is called Square 3, which consists of 12 satellites in 3 orbits with 45 angle shift. So in each orbit there is a square configuration. Such configuration allows to improve the gravitational wave observatory response to all the gravitational waves possible directions. The requirement of a SOIGA project is sensitivity to the gravitational waves with amplitude no less than 10 to -19. The normalized transfer function, dependent from frequency for different configuration of space antenna, is shown on the figure. On the next slide, you can see the mass frequency diagram for SOIGA 2 project. The frequency range from 10 MHz to 10 Hz is very interesting because it is on the border of ground and space detector projects. Implementation of project in this range will make it possible to observe double star system with mass from 1 to 100 on interval from 1 day to 1 minute before merging. It is proposed to calculate in SOIGA 2 project the binary systems masses using equations obtained by Vladislav-Ivановich. The main difference from current approach based on Newtonian approximation is that the highest frequency is not required. It should be noted that the highest frequency value corresponds to the moment of time immediately before the collapse of the binary system, when the values of velocity of the merging black holes becomes comparable to the speed of light. And the speed can reach values of 0.4 to 0.5 light speed, and relativistic corrections become very significant. In the approach proposed by Vladislav Ivanovich, only the minimum value of black hole rotation frequency is required, which is equal to the Hall signal frequency detected by gravitational wave observatory. To the spacecraft are applied different disturbing gravitational and non-gravitational forces. The gravitational forces impact both on spacecraft and test masses and cannot be compensated. This leads to variation of interferometer arm length or displacement measurement. The value can reach thousands of meters. However, the gravitational disturbance have different frequency spectrum compared to gravitational wave observatory. So these forces can be pre-calculated and excluded from interferometer measurements. The non-gravitational forces can have overlapping frequency spectrum with gravitational wave observatory, and variation of intersatellite distance can be up to fractions of millimeter. But these forces are applied only to spacecraft, so to exclude non-gravitational forces in SOIGA is proposed a drag-free system, which is analog of LISA system. It is proposed to use both interferometer and capacitive sensing for measurement of the test mass position in the satellite. Disturbance accelerations should be reduced to 10 to -15. The SOIGA's intersatellite measurement system uses the Michelson interferometer with arm length of 36,000 kilometers. The aim of SOIGA project is detection of gravitational waves with amplitude no less than 10 to -19. So the desired resolution of intersatellite interferometer should be 1 picometer and better. The design of interferometer is proposed similar to the lasers. On this slide are listed the main sources of intersatellite interferometer noises. The present report describes an improved Russian concept of space gravitational wave detector SOIGA-2. SOIGA-2 is proposed to be located on the orbits of GLONASS. The aim of project is to detect gravitational waves in frequency range from 10 MHz to 10 Hz. Implementation of the project in this frequency range will allow to observe double star systems with mass from 1 to 100 solar masses in the time interval from 1 day to 1 minute before the merge, as well as the evolution of binary systems. Different space gravitational wave observatory configurations are reported: orthogonal, triangle, square, octagon, and square free. Requirement to drag-free system of test masses is residual acceleration no more than 10 to minus 15. The value of non-gravitational acceleration applied to satellite is about 10 to minus 7. Analysis of disturbing gravitational forces impact on test masses is reported, and requirement to resolution of intersatellite interferometer is 1 picometer and better. The reported study was funded by RFBR, the project number 1929-11022. Thank you for your attention.